or just talent strategist. Keyword matching fails here because the exact words may differ even if the meaning is similar. That's why we rely on semantic similarity instead. And, and here's how we can approach it. Each candidate gets assigned a fit score between 0 and 1 based on how similar their job title is to the search term. The score is calculated by embedding the job title and the search term into vectors. Also, measuring the cosine similarity is the key point rather than using Euclidean distance because of the cursive dimensionality. In high-dimensional spaces like embeddings, Euclidean distances tend to lose meaning, whereas cosine similarity remains robust in capturing relative orientation and semantic closeness. So ultimately, the higher the cosine similarity, the closer the meaning, and the higher the predicted fit score. Next, I will go through the word embedding methods, how I dissect the words into words so that I can put into the model.
Can I ask a question?
Sure.
Don't you have any visualizations to kind of show us directly what you're kind of describing as opposed to you just saying it?
Yeah, I do have in my code.
It kind of makes you follow a bit better then, because obviously we're imagining as opposed to seeing like where you start and you finish, or even your results.
Yeah, sure. So, and due to the limitations of like screen sharing, that I'll go through the presentation slides first, and then go to my Google collaboratory notebook. Yeah, sorry, I should have mentioned earlier. And in this part of the project, I applied four different word embedding methods. And the first one is TF-IDF factorization, word-to-vec, globe, and fast text. Yeah, remember that the goal throughout is the same, to convert job titles into meaningful vector representations and compare them to the search term, and then generate a fit score based on semantic similarity. To explain about turn frequency, it stands for, and it is short for TF-IDF. And it's a classic technique that measures how important a word is to a specific document relative to a collection of documents. In this case, each job title is treated as a mini document. So the search term, for example, aspiring human resources, is converted into a TF-IDF vector, and so is each job title. Then I used cosine similarity to compare the vectors and calculate how close the job title is to the search term. And so the TF-IDF doesn't understand the meaning, but it's a good baseline for me measuring keyword overlap between phrases. And the next step is word-to-vec, which I'll also go through my code after the presentation. The next embedding method I applied was word-to-vec, a more semantic word embedding method developed by Google. It comes into two flavors, CBAL and skipgram. In CBAL, which stands for continuous bag of words, the model learns to predict the center word based on surrounding context words. In contrast, skipgram does the opposite. It predicts the surrounding words given a center word. CBAL is faster and works well for frequent words, while skipgram is better at learning rare or nuanced words, and which can be important when dealing the job titles that vary across candidates. In this project, I applied both versions, embedded the job titles and search terms, and calculated cosine similarity to assign the fit score. And when you just listen to the theory, you might not understand fully. So I'll also show how they work differently in code. The next step is global vectors, which is short for globe. So unlike word-to-vec, it learns from predicting context in local windows, and it uses global word co-occurrence statistics across the entire corpus. It builds a word-to-word co-occurrence matrix, essentially counting how often words appear together. And then it learns the embeddings that capture their ratios and patterns. For example, the ratio between HR and the recruiter might be close in many documents, so their vectors will also be close in the global space. In this project, I used pre-trained global vectors to embed the job titles and search term, and once again calculated cosine similarity to generate a fit score. Next step is fast text, which developed by the Facebook AI research. Unlike word2vec or Globe, which treat words as atomic units, fast text breaks words into sub-word units, specifically character level and grams. This means even if the model hasn't seen the exact word before, it can still generate a meaningful vector by combining vectors of its sub-word components. For example, for the word recruiter, fast text might extract words like recruit, and ter, and so on. These sub-word vectors are then averaged to create the full word vector. This makes fast text especially useful for handling typos, rare job titles, or morphological variations, which are quite common in real-world LinkedIn-style profiles. Just like before, I used cosine similarity between the embedded job title and the search term to compute the fit score. Yep, and these were the summarizations of the 4 embedding methods that we just go through. The next step we should go through is this learning to rank the candidates according to their fit score. We move beyond fixed similarity scores and introduce a learning-based ranking approach. Instead of only comparing job titles with a search term, we want to model to learn what makes a top-ranked candidate based on human feedback. For example, by studying an ideal candidate, we use a method called learning to rank, and specifically lambda rank to train a model that can produce better ranked candidates lists over time. And here's how lambda rank works in this project. For each candidate, we generate an embedding of their job title. We also embed the search term, then we calculate a score and rank the candidates. If a human reviewer stars a candidate, we treat that as a supervisor signal, and we train the model to give that candidate a higher score in future iterations. Over time, this helps the model learn what kinds of candidates are most relevant beyond simple keyword matching.
Can I ask a question?
Yeah, sure.
So this is like candidate tracking software, similar to application tracking software, yeah? So you obviously need applications to get this type of information for you to get the variations of who will be the most suitable candidate.
Quite similar. I don't know what the applications you mentioned means here, but it's more like ranking to rank the candidates according to the fit score.
Okay.
In a real scenario, there is generally a PDF document which is uploaded by a candidate. So how do you do the extraction relevant? What are the relevant roles so that you can match it?
To explain the method, I think I should mention about like some mathematical like principles of lambda rank. And yeah, is that the question you are asking? Did I understand your question correctly?
Basically, in a resume, there are a lot of text. So, what is the role which needs to be like? Which text needs to be matched with the role to find the relevant candidate? That's what I want to know.
I get it. So I set the search term as aspiring human resources or just human resources. And based on the search term, I set that as a standard search term, and the most highest score, highest score based on the search term would get the highest fit score.
Okay, so the searching will all be done by the lambda index, and we are not responsible for what part of the resume it searches and all.
I think yes, in this project. If it comes to the real world project, I would probably like set the search term based on the most frequently mentioned vocabulary after dissecting all the data.
Okay, got it. Thank you.
Yeah, we finally get into it, the real part of language models here. And generating contextual understanding, not just counting words. That's what LLMs do. And so far, we've been using like fixed word embeddings and statistical models, which might be a little boring. But what if the model could actually read the job title and understand its intent, just like a human reviewer? That's what we aim for in this step by applying large language models. And when applying the large language models into the real world data sets, we call that as fine tune. We define them as fine tuning. But here, LLMs aren't magic. As you know, our reality isn't a drama where we throw in a few prompts and get perfect answers. In fact, in this project, every step had to be built, tested, and refined by hand. I tested several models that looked promising on paper. But here's one important note. Since I was working on Google Colab, I was limited by computing capacity. So for each model, I choose the smallest parameter version, usually around 1 billion to 2B, and always use the instruct variant, not the chatting version, because instruct models are better suited for structured scoring tasks like this one. So I began with Mistral, and popular for its speed and open weights. But it didn't produce reliable scoring. It responded in general terms or repeated the same outputs. So I tried B for the next time, a lightweight and simple, but again, it failed to distinguish between different job titles and the outputs lacked depth. Then I moved on to Queen, hoping the multilingual training might help, but it either gave everyone the same score or ignored the prompt structure altogether. Finally, I even used GPT-4 through the OpenAI API, expecting a gold standard result. But even GPT-4 returned vague responses, and since I was using the API, I had no way to train it or control the output behavior. That's when I realized it's just not what model I'm using, but how I should use it, and that changed quite a lot. So here's the two ways you can apply LLMs through an API or direct download from the open source like Hugging Face. For example, they might look similar, so I give them a prompt and they return a response, but understand the hood, they are completely different. With an API-based model, I'm basically sending a prompt to a server. The model is running on someone else's infrastructure, so I can't touch the weights. And that means I can't teach it anything new, and I can't fine-tune it for my task. But with a downloaded model, I have the weights on my own in my notebook, the architecture and the tokenizer and the everything. That means I can run LoRa and apply parameter-efficient fine-tuning techniques, fine-tune it with my own data, and make the model learn what I want it to learn. So if you want a model to adapt to your specific task, like assigning a fit score between 0 and 1 based on a candidate's job title, downloading the model is not optional. I think it's essential. That's when I fully switched gears and from API testing to model fine-tuning and eventually found Olmo, which comes to the next slide. As I mentioned before, I failed many times using other models, and I finally come to the Olmo. It was released from AI2, the Allen Institute for AI, and is part of a family of models designed to be open, transparent, customizable. Remember, I'm not advertising, but just walking through my experience. And for me, Olmo did work well. I used Olmo 1B to fit within Google Colab's computing limits. Since I wanted the model to learn how to assign a fit score between 0 and 1, I fine-tuned it on a data set I constructed based on candidate job titles and search terms. For the fine-tuning, I used LoRa, a lightweight adapter based method. LoRa allows you to train large models efficiently by only updating small components, so it works well even on limited GPUs like those available in Colab. After training, I used the fine-tuned Olmo model to predict fit scores for new candidate job titles, and this time, the results were finally aligned with expectations. Instead of vague answers or uniform scores, the model was able to assign differentiated scores that reflected real semantic similarity. Also, now that we have a fine-tuned model that can generate fit scores from the job titles, what if we added more context to help the model reason better? That's where RAG, the retrieval augmented generation, comes in. And it comes into two ideas. First, retrieval. It fetches relevant documents or snippets from a knowledge base. Second, it's a generation. Then it lets an LLM generate responses using both the prompt retrieved context. In our case, we could build a custom knowledge base of role descriptions, hiring criteria, or ideal candidate profiles. When giving a candidate's job title, the model could retrieve the most relevant expectations for the role and generate a more informed fit score. This way, we move beyond the surface level matching and build a system that can reason with external context. Yeah, thank you for listening. And this is the end of the slide, but not the presentation. Before we move to the real notebook, the code, do you guys have any questions so far? If no, I'll go through the notebook quickly.
You explained in different ways here that you had to search for models or some type of software that enables you to have like better search methods. How many languages, how many models do you use there? Or is it just you looking for software that's compatible with your model?
I used at least four, and I also walked through many models on Hugging Face. I think I can't count, but about like 6 to 7, I guess.
Okay. So what do? Do you combine all that information into one model then?
Not really. I used all the model in a different notebook. And yeah, as far as I know, there is a method to combine all the pros from the models, which is called the ensemble method, but I haven't applied in here.
Okay.
Yep. Any other? If there's no question, then I'll go through the notebook.
I think we have a question, Yoojin. Japet has a question, I think.
Oh, sorry.
We can hear your question.
Sure. Sorry for that. Well,
you are muted, Japet. We cannot hear your question if you're talking right now.
Yeah. Hi, Japet.
Hello. I have a question. I wanted to confirm what exact dimension would be a better choice for transforming or training the text.
I'm sorry, I didn't understand your question fully. Could you repeat one more time? I'm sorry. Oh. Yep.
Hello. Can you hear me?
Yeah,
yes, we can hear you.
Yeah, my question is, what is the optimal choice for the dimension when we are doing the embeddings?
When I was working on embedding here, I only applied the three data. I only applied like 3 columns from the data set we were given, and those were job title, and the fit and job title and the search term, and yeah, I have one more thing, but I can't remember. So maybe I can answer your question when I'm showing my code. And I'm trying to. There were 3 inputs, and the only output that I was focusing on was the fit score. to calculate how much each candidate is fitted to the search term that I have set. Is that fine for you?
Okay, that makes sense.
Regarding
Also,
embedding, there are multiple models which can generate embedding. So how do you choose which is the best model to embed based on your project?
Yeah, I think that's a good question because I also worked on many different models as well. My answer could not be the perfect answer, but so far I have trialed and failed for like 6 to 7 and that's how I find the appropriate models in here. But I do not like highly suggested my method, my strategy, because I have failed quite a lot of times to find the appropriate one.
Okay, yeah, thank you.
And I can
we
read
have
the
a question.
Mhm.
Eugene, in the chat box, Japeth is asking, you mentioned you had limited GPU in Collab. Which GPU were you using, if any?
Oh yeah, so when finding the best model, I didn't like pay for the Google Colab, so I used the free version of Google Colab. And as far as I know, the free version has only like few GPU capacity. And I tried the highest one, the T4 GPU. But when I worked on Olmo, the last one, the last appropriate model that I find, I paid for the Google Colab and I use A4 GPU.
Thank you. Also, Leroy, I think, has a question. Go ahead, please. You're muted if you are asking your question right now.
Sorry. Have you ever tried Amazon's large language models before?
Oh, no. But if I knew they have one, I would have definitely applied for that one.
Sure. Okay.
I think that's all for now, Yoojin.
And I'll go through the code part, which is ready in another in my other screen. So could you hold me for like few seconds?
Sure.
Yep. So first, I'll go through the word embedding, the 4 steps that I worked on. Here, I haven't like run it, but already the consequences are already saved in here. So I'll go through my notebook. As I mentioned, that we have worked through the 2 big process. The first part is embedding, and then use learn how to rank. Yep, and I mounted my G drive. Also, go through the package installation. And since I was working on this project step by step, I worked on EDA and data processing as well. So this is the data that I have used, which is also uploaded on the project 3. For the EDA part that I haven't like put it in my presentation slides, I I try to check whether any data is missing, as well as the whole numbers of data, the rows, and try to visualize into word cloud so that I could see how frequent each vocabularies were used. And you can see that aspiring human and human resources shows the biggest size of these vocabularies. So I set them as standard search terms. For data
Yoojin,
processing.
so sorry for the interruption. Could you zoom in your screen, please? I think people have difficulty in seeing. Thank you.
Does it work for you?
Thank you so much.
Yep. So these are the first steps for embedding methods that I walked through. And vectorization, as you can see, I use the TF-ID vectorizer, which is a default method in applying such package, as well as try to transform the job title into the vectors. Each number, each decimal point implies the job title, the vector values of the job title. And the numbers of these rows might probably, the 103 means there are 104 people, 104 candidates in this data. Yep, and try to vectorize and put them into TF-IDF metrics, as you can see, and put the max features as the default value, which is 100. For the first search term, I set them as human resources and then aspiring human resources. But I bet this is a bad code that you can hard code to explain how different values they can show. But when you code in your own notebook, try not to use this way, but just change them. Yep, you can definitely see that the first search term, the values of the first and second and the third search term shows different values each. And try to apply the cosine similarity based on the TF-IDF factorization, which and try to rank according to these values. When applying TF-IDF, the number 73 shows the highest cosine similarity score. And as you'll check that each method shows the different ranking score that shows the different people in ranking. Yep. And for the word vec, as mentioned in my presentation, there are two big different methods, which was CBAL and then skipgram. First, I tried to apply a continuous bag of words and print aspiring and seeking in separately. Yep, as you can see, each word shows each vocabulary shows different values here. And this is the embedding, the consequences of embedding, and you'll put them into you'll apply into when you apply this into to calculate cosine similarity, it also shows the different person who has the high score. Then we'll go to the skipgram. I also worked on aspiring seeking and shows that this is the consequence of different values of different vocabularies, as well as different embedding vectors. Also, different people appear as the first candidate, first highest fit score. Next one is GLOBE, the global vectors for word representation. When I firstly tried to download the package, it doesn't get installed properly. So I download it manually by getting into the Stanford homepage and then open the zip file in here. I use the smallest parameter because of the GPU capacity, and also worked on embedding, and this is the consequences of embedding vectors. And try to apply the mean when calculating the vectors. And the consequences of search term global embedding. And then apply cosine similarity. And since this one doesn't show in here, I'll open up as my CSV, which is saved in my G drive. Yep. You can see also that different people shows the highest cosine similarity, different from TF-IDF and Word2Vec. They all have the different fit score. Yep, and you can see that Aspiring Human Resources shows the highest score in here. Coming back, yeah, the last one, it was fast text. And I keep the search term as Aspiring Human Resources as well, since this is a pre-trained model that I have to download the model to work on fast text. Yep. For the fast text, for me, maybe I am a bad coder or not, but it shows the whole people the same score in here. So I try to work on the rank fit and sort them into the ascending, and give them as false. But still, they have showed me. They have shown me all the almost same fit score for everyone, but applied the 48 people on the first rank in here. Yep, and the next one, yeah, and the last CSV that you can see in here was all the merged one. That has 13 different columns. Can I just zoom out? I'll zoom out just for a second to show you this whole CSV. Yep, this is the merged version of the whole data frame. And yep, this is it for the word embedding. For the learning to rank and lambda rank, I'll also turn on my, I'll also share it on my screen. In here, I would skip the EDA part. And among the different data frame I have made, I choose the fast text one. because it was the latest model. In this version, I applied the appropriate, the cosine similarity fit score shows the appropriately, so I choose the best text in here. And this is how the model works in here. I try to pairwise the data and try to like append them into a big data frame so that the model can use my data input appropriately. And I put input size as 1 so that it could be more, so that it could contain more features. This is the model part, and worked on model, run the epoch for 500. Final ranking shows that the highest score with 0.9875 shows the highest, has the first rank, and this is the consequence that resulted in the descending order. Yep, and for the side project, for the side code, I also worked on, I also tried to print out weight and bias to check the model. So far, this was the step 2 learning to rank, and then would also show you lambda rank part. Again, in here, I choose best text for best text version of data frame. And then normalize the fit score to put it into a model. Yep, this is in here, it was the architectural part of the lambda rank. And I tried to, which is simpler than the learning to rank. And then initialize weights, and then work on, and then training. And work on train the model for setting the epoch as 50. And try to print out each weight and biases so that I can check whether the model runs appropriately. And then work on the ranking, and it definitely shows the different results from learning to rank, that the highest score was 0.7342. And then sort it according to sort the candidates into a descending order. Yep. Oh, yeah, I see. I saw someone was raising hand. Please go ahead with your question.
How does the machine define the score of the candidate? What exactly is it looking for?
I tried to keep a note of how these two models work differently, but my answer could not be like perfectly answered your question. But as far as I know, the lambda rank uses the lambda rank calculates the whole entire list of candidates at once, while the first one, the learning to rank, work on pairwise data. So they check the two candidates. So they so for the learning to rank, they pair the data into two and then keep comparing each of the pair. But for the lambda rank, they consider the entire list of candidates at once, and they use and then optimized for ranking-based metrics, which is called normalized discounted cumulative rank. And that's how they work differently. That's how they work.
Is it based on skill set or experience? How would it know? How would we define the person to be the best candidate?
I'm sorry, could you repeat the question?
Is it based on the candidate's skill set or experience? Does it do it that way?
I think it's based on candidates' skill set and based on how they have like written on their profile, because the model only like looks for specific search term, like aspiring human resources or human resources. But I think in a real world, it doesn't really. In the real world data, I don't think the HR people would only like look for the term people have set. But in this project, we only like focused on the search term.
Sure.
Yep. I saw another person raised his or her hand.
Can you hear it?
Yes, I can hear you.
Okay. I saw that research student is ranked higher than other HR candidates.
Mhm.
How does that work? In the list of Lambda rank, I have seen that research student is ranked higher than other HR candidates. Can you show the list of Lambda rank? Yeah. Yeah, at 10, the number 10.
Mhm.
Wait, not number 10.
Oh, so you're asking whether this one is the first person or not? Is
Yeah,
that?
I did
Yeah.
see.
When printing out, I haven't print out the original index number of this candidate, but just put the rank number in here, and try to like compare the
Okay.
job title. Mhm.
Okay.
Yeah. So as you can see, definitely here comes another person in here, as well as the fit score. And for the lambda rank, yep, different person in here.
Okay. Okay. Got it.
Yep. Yeah. So far we have like gone through the step 2, and I'll share how LLMs works in code. I actually don't know what to open from the models that I've worked here. I've worked on Phi and Olmo, Mistral, Llama, Grok, DeepSeek, and everything. Yeah. Then I'll open this one. I first applied Grok API AI. And here it's the important thing is that you really need to download the necessary package, which isn't like set as a default function. In here, I try to. Oh yeah, so here's the API token, which should be kept a secret, but I hope you guys don't copy this in here. And there's another way that you can access the API through a notebook by not like showing this into a code. That Sammy told me that you can use the key on the left side of the column and put the API, set the name of the API and put your token in here. Then yours is hidden. Work on LLMs, and you'll also get to the fit score. And for this version is the failure version because the fit score doesn't like appropriately calculate. But try to show you that how this LLM works on code. Yep, and another version. That one is the model that I use API, but there's another way that you can download directly from the Hugging Face. I'll open this one. Same, you need to download the necessary package, open the source, open the data, and here since I have to connect with Hugging Face, I log in with the tokens. When you run the code, they ask you to put your token in here, and I did it so that you can hide your token. And also a way, I think there's a way. Oh, I think I didn't upload it yet in here. Maybe it works same in here when you give the token and access to the notebook directly. I also choose the instruct version from Hugging Face, and this was and the 8 billion was the smallest model among the llama. Yep, and you can see the job title. You can only check the top job titles, excluding index. Or gone job titles and prompt it. Yeah, after downloading the model, I trained it and prompted, but wasn't properly trained, and shows only the 5 people in here, which is another failure version. So I tried to apply. Yeah, I'll stop showing you the failure version and show you the successful one in here. I applied Olmo. Sorry, just for seconds. Yep.
I was going to say, I kind of get what you're doing now. Is the purpose of this task is to use various different models to define each of the 4 steps to do with the candidate profiles, correct?
Have right and need to be more explained in detail for another half. My purpose is to share my experience and then show you how to apply models appropriately, rather than just sharing my experience.
Okay.
But I go through my failed experience first to show how to find the appropriate version. Yep, and this was the appropriate version. I actually run it right before I start the presentation, even though I have a good fine-tuned version. Again here, I installed libraries to LLM fine-tuning and OpenCSV, and then I tried to merge and augment the data set so that my model can work more properly. So far, I haven't before this trial, I didn't merge the data, but it's another data that I was given to work on model. Same here. All the job titles, all the columns that I've applied were still same. ID, title, and location, and screening score. And I also applied, the important thing in here is that I convert my CSV into JSON-L data to put into the model, and the model works better. So I use the smallest version and then instruct version of the model, download it and tokenize it and trained well and ran it when I was presenting my slides, the model was training. So sorry that this is still inferencing and working, but the model shows the rank perfectly, and the fit score was calculated according to each candidate. I'm sorry, this isn't already. Yep, and I also try to show you the rank part of it, which I was working on it and will be work on the future. And yep, this is so far I have prepared. Thank you for listening to my and asking questions to my code. Are there any more questions?
So I don't have any questions. I think only one, but thank you so much, Yoojin, for presenting. It's just that overall from all this that we have gained, is it true that we would have to have a very high level of understanding with topics such as math, specifically trigonometry in this case, the sine, cosine?
Could you repeat only the last part of your question?
So do we need to have a very high level of understanding with trigonometric concepts like sine, cosine?
Oh, I don't think I need to, because personally, for me, I'm not a math major as well, and only try to understand why we use cosine and how it works on it here. You don't have to be like math expert.
Okay.
Yeah. I'm sorry that this model is still running, but try to show as much as I can share you. When you, yeah. Oh wait. So I set my directory, and the fine-tuned version of models is also like saved in each directories. And this is the recent one that you can like take out your model checkpoint. So this checkpoint and the number in here shows each different version of the trained model. So you can like recall this version when using inference. Yep, and the logs will also be saved according to the directory you have set. Yep. Yes, Sammy.
First of all, thank you so much, Yoojin, for this fascinating workshop. It was very informative. I appreciate you taking the time to walk through the stages of your solution and the project. I think like there is a spreadsheet. You can like leave your contact information. It's great for networking with people who joined the workshop today. But one thing also could be also very helpful, I believe. Maybe like the Apziva team can share the repository, your repository, like once you wrap it up. I think people who are curious about looking at the code, it could be also like quite helpful. But I mean, thank you so much. It was really nice listening to you today.
Thank you too, and thank you everyone for listening to my presentation. Yeah, I'm signing in my GitHub, which I have shared all my journey on it, and we'll leave it on the comment.
So I think we have one final question. And Ellison asked, how long did it take to complete this project, Yoojin?
That could be differ according to what tasks I was working. As a whole, I think it took like 2 to 3 months, I guess, since starting project 3. But for each step, for the first step, the word embedding part, it take me about like 2 to 3 weeks. And for the second step, I think it only took 2 weeks. But for the LLM part and the fine tuning part, it took me a lot, like less than 2 months, I guess. Would that be an answer for you?
Thanks for the answer. That, I think, brings us to the end of today's workshop. A huge thank you to Yoojin for sharing her insights and walking us through the process of building a generative AI candidate ranking system. It is always inspiring to see the work of our Apziva residents. And this was our first Apziva workshop, but definitely not the last. So stay tuned for more hands-on session where we will continue to explore cutting-edge AI and data science topics with the industry expert Apziva alumni and Apziva residents. Thank you all for joining us today, and we look forward to seeing you at the next one.
Take care, everyone. Bye.
Thank you.
Bye-bye.
And please fork my repository. It will be keep updating.
Mhm.
Thanks. Yeah, seems like my model is still inferencing.
Yeah, it
Will
takes a
give
lot of
also-
time. It takes a lot of time to train large language models.
Yep, thanks. I'll leave the chat.